Yeah. So when I do these sessions, what I tend to bring is a few topics that fall into this bin that I call platform topics for modern DBAs. And so I'll be covering some things that span the hardware platform that I happen to work on, because it is platform topics for modern DBAs, and I think it's interesting stuff. I'll slide from that into some topics about modern Intel hosts. We'll look at some ways to use Slob and interesting test scenarios. Yeah, and stuff like that. Just the show of hands. How many people here test platforms with Slob? Okay.
What's Slob?
It has an acronym, but it's rated R, I can't tell you. Yeah, so there's enough of us here that know what Slob is, and the rest of you will, of course, feel compelled to go run and check it out afterwards. First thing I want to do, however, is I'm going to walk through and say a few things about Extreme I/O, because I'm the performance architect on this product line, and I'm very excited about it. The previous slide I just didn't show you basically says how popular the product is in the marketplace. It's really popular, but I like to talk about why it's successful. It's successful first and foremost because of its scalable architecture, and this is interesting stuff if you're a propeller head, so we'll go through it. Typical storage products today attach with some kind of storage area network on a protocol of Fibre Channel or iSCSI or whatever. And generally what you'll have is an active controller and a passive controller in case one gets shot in the head with a 20 millimeter. And that's not really all that scalable. Really, the other controller is just there to pick up in case the other guy dies. And then downwind of that, you'll have flash assets. And your read and writes flow over the storage network protocol naturally. So the difference between that and what's on your right is the modular building block for Scale I/O is called a brick, an X brick, and it has two controllers, and each controller has two Xeon CPUs in it. Each of them are 10 core CPUs, in fact. And then if you need to add either compute power, and I'll explain what compute power is later, well, in short order. If you need to add compute power or capacity, you have to add more bricks. So you can't add capacity without adding performance with this architecture. So by the time you're done with the current maximum size array, you'll have 16 controllers. And like I said, each controller has two CPUs in it. So it's a very compute-capable storage platform. I'm going to talk about what compute-capable storage means in a moment. The other thing about this product, and it's the number one reason why I don't hate it, is because it's extremely simple. Complex storage needs to die. There's no reason for storage to be complex because we live in a world now where you don't have to have seeks before you do reads and writes. And if you think about it, the number one reason storage has been so complex historically is because you've had to do a lot of things to mitigate the cost of seeks. Well, if you free yourself of a seek environment, well then the storage should become, quickly should become simple, and that's the way this product is. So the first thing that's easy about it is how do you provision? You don't have to think about geometries of things like, you know, the storage devices and what internal controller arm they're on and all of this stuff. It's nothing. You just walk up to the management GUI and you say, give me a volume of this size and provision it to these hosts. It's literally 3 mouse clicks, and if you can't do it in 15 seconds, it's because you've been hanging around with Mullins too much. So, the other thing about this product that is very...
It makes you stupid.
Yeah.
I just want to clarify secret use.
If you... the other thing about this product that is very exciting to me is its copy data management and data reduction services. That's a lot of syllables that basically apply to this. So this is the craziness that is an SAP landscape. This is complex, and the thing that has to address this kind of complexity is weeding out the costs of copies, because there's tons of copies. You've got your production, and then you've got test and QA copies, and when you're tired of those copies, you make more copies, copies. And of course, there's multiple applications, so everybody loves some technology that makes their first or second copy easy, but generally speaking, that technology will only make copies simple until you have 4 or 5. Well, we're talking about a product that can handle thousands upon thousands of copies, and I'll talk in a moment about why that's possible. So here's an example. You know, if you have production that's requiring 20 terabytes of storage because it's RAID 10, and alongside of that you got 5 copies of test eating up 60 terabytes of disk, and then RAID 5 for development is 12 terabytes, so 92 terabytes of disk, really just to deal with a 10 terabyte application when it comes down to it. So all of these brute force copies and what have you, this is the problem that this product solves. I'll say another word about that in a moment. But first, I want to go through and talk about the absolute fundamental reason that this storage product is different than any other storage product. I've already mentioned scale out. I want to talk about how it scales out and is predictable in its I/O service times. And I'm not touching anything, but it's just moving through. So here, okay. So the thing about Extreme I/O is it's a content-aware storage device, and what this means is, because of content awareness, we have techniques that ensure that all data is laden upon all SSDs equally all the time, and therefore all of the metadata operations for the data that's stored in the SSDs are handled equally by all of the storage processors. So the CPUs never go spiked on one end and underutilized on the other. Everything is very symmetrical in this device, and we'll show how. So when data comes into the device, the first thing that the storage controllers do is they compute a universal hash on the data that's in the block. And that hash value does a lot for us. It allows us to establish where the data is placed. First and foremost, which brick it goes into, and then secondarily from that, which SSD it goes into. So the way it works is you can just think of sort of like there's a fingerprint prefix, data comes in, and it finds its way down to bricks, like this crazy animated slide is going to show. Where's the soundtrack for Jeopardy? Eventually it'll get to the point of me pointing out deduplication. So yeah, so here's the way this went. All of this data came in to the array, and you didn't have to think about what the contents of those blocks were. Were they undo? Were they regular data or index segments? Was it redo? Doesn't matter, because the data comes in and we compute our hash on it, and based on that we will place it on a brick and then secondarily to that an SSD. Anytime data changes, it will always go to another SSD. So even if you have, you've got one hot block in your database and you update it, the SCN gets bumped in that. So even if you update it to the previous value, so you didn't actually change any data, you have changed the block, and therefore it'll end up on another SSD. So you can never have one of the SSDs in this device. There's 25 SSDs per brick. You can never have one of these SSDs that's getting overburdened. I'll show that. So the duplicate gets thrown away. Great. So this is, because everything is symmetrically placed in the device, that means that all of the metadata that helps us do things like deduplication and handling our compression mapping and all that stuff, the CPUs, if you monitor the CPUs on this device, you'll see this really boring graphic. All CPUs are always equally utilized. Snoozer. As far as fill levels in the SSDs, this is showing that, this is an array that has, what is that? That's probably a 2 brick array. Each brick has 10 terabytes. So this is a 2 brick array, and there's only 0.16% variation on how full the SSDs are. And this is the way all of these SSDs are. It doesn't matter what your application is. It could be SQL Server or Oracle. It could just be whatever. Because of the way data essentially hashes out fairly, to a very large bitmap, or to a very large space map, I should say, you're guaranteed that even constantly writing the same data, you're going to fill the SSDs equally. Get through that before I put you to sleep. Okay, and then the other thing about the content awareness, because you never have one SSD that is overburdened compared to others, we wear these SSDs down equally. In fact, we have call home data from all of the thousands of these things in the field. We actually don't have a single array in the field that has less than 20 years of life left on it, because all the SSDs constantly tell us what their remaining endurance is, and we keep a database of that. That's because you can't pick a place to put your data and overburden an SSD, broken record here. So yeah, they're all greater than 95% life remaining. In fact, most of them have 20 years left on them, but people don't use them that long. Okay, so predictable performance. So this is actually the value of having symmetric controllers handling the data. When we go up against a standard active-passive controller array, generally speaking, we and they will offer about the same IOPS, but that's not the hard stuff. Because everybody knows what Flash is good at, right? It's good at reducing the seeks and reading and servicing reads. That's what Flash is good at. Does anybody know what Flash is absolutely horrible at? Writing data. Your database people. Databases write data sometimes. So this is the hard stuff. If you don't do Flash correctly, what you end up with is your writes will suffer massive spikes. And they suffer massive spikes sometimes architecturally because they've decided to implement the array using just plain NAND Flash and have a host level or a controller level software program that deals with the garbage collection that's involved with writing on Flash, because Flash doesn't want to be written to. It's a necessary evil with Flash, and so you end up paying tax and garbage collection time. So these things cannot happen on our device. Okay, copy data management. I'm going to go through this quickly. Okay, so look, we have virtual copies, and we used to call them snapshots. The reason we stopped calling them snapshots is because they're not like anybody else's snapshots. Okay, so you have to come up with a new name. Extreme I/O, so look, it's already a global dedupe. We never put metadata on disk, it's always in memory. And because of this, we have the underpinnings for doing copies of data in a very intelligent fashion. The virtual copies do this. So if you have one Oracle database, and you make an Extreme I/O snapshot or Extreme I/O virtual copy of that, that takes up no space in your array, ever. There are a lot of storage products that when you create a snapshot, it also takes a little space in the storage array for metadata to map that, and then the device has to read the metadata in from storage in order to figure out what to do with the application data that's in the snapshot. So it's a double whammy. It takes capacity from you, and it takes performance away from the array, okay? This product always has in-memory metadata, and copies are absolutely free. So every volume you can copy 512 times. You can have 8,192 total copies in the array, and you'll never see I/O for metadata. It's always in DRAM. But you know that you don't just copy data and leave it static. You sometimes change it. So if you change, let's say 20% of one of these snapshots, these are read-write snapshots. Oracle has its downwind of host adapters, and Oracle has no idea that it's in a snapshot. Everything works just fine there. But if you change 20% of the data, we then, as you change that data, we then apply dedupe and compression to it. So if you change 20% of the data, it doesn't mean you're going to inflate or take 20%, that 20% from the available storage pool. You might only take out of 20%, you might only suffer 8 or 10%, or even less. It depends on how sparse the blocks are. So the point there is copies are free, and even as you modify copies, snapshots, even as you modify snapshots, all of the changes, we do all of our fingerprinting, dedupe, and compression. Interesting technology. Okay, the final bit of this segment is, we have customers that actually use this stuff, right? These guys I'm particularly fond of because this is an Oracle use case. Before they were using our stuff, they had to use 125 terabytes of storage for their 50 copies of their database, and now they use 4 terabytes. the slide says it all, so I'll just walk out. No, I'm done. Okay, 31-to-1 overall reduction. Okay, quick word about this. Data as a service is becoming very popular. There's folks in this space, Delphix, sponsors of this show, they're in this space. So Extreme.io plays in data as a service as well, and there's an add-on product called AppSync that it allows you to broker permissions so that anybody that you allow, anybody can copy a database, and you can vector out whether or not they can copy production or copy this, that, or the other. Developers can go with a couple of mouse clicks and copy a database, and after they use it for a while, with a couple of mouse clicks, they can refresh. They can refresh to other people's copies, so if there's collaborative work going on and I want to catch up to what you've been doing, I just simply refresh from you. All of that stuff is done through a GUI and is self-service. So the thing to do is just make a mental note of this. This is a good way to go and find a video that I did that demonstrates the product. Just ask Google to find Kevin space database. It'll take you to my blog, and then you'll find this. Or go over and get some free stuff from EMC, because across the street from Moscone West, we actually have a 3-story building over there full of EMC stuff, and we'd be happy to see you. That's the message from the sponsor before I move on to the stuff you actually came to listen to. Okay. So the thing is, you can go over there and see a live demo of AppSync self-service clone copies of data. All right, I'm going to jump over this in the interest of time. Okay, we'll get to platform topics. You folks remember that year we were here? It was probably 3 years ago or so. It was about 115 degrees yeah. Platform topics. Okay. Here's what I'm going to do. I'm going to talk about Slob for studying database contention. And those of you who know Slob know that that's the opposite of what Slob is supposed to do. So you should go, well, maybe I can pick something up. I'm also going to show some methods and some data, studies in filtration and projection CPU costs with parallel query. I'm going to use a simple schema just to help get through the information. But the whole idea here is I run into a lot of folks that don't know how powerful modern platforms are. And I'm going to show some techniques and a few measurements to show how powerful these platforms are. That's kind of where I'm at with this. And then I'm going to say a word about Swing Bench. I'll probably just say Swing Bench. That's a word. So, no, I'm actually going to say a word about Swing Bench. Slob for studying contention. By default, Slob is architected to produce what? Maximum IOs from as few cycles of DB CPU as possible. That's what it does. Now, if you can find me a kit that produces more IOPS per DB CPU, tell me about it. Because I've been going around as if I know this is fact and telling everybody that they'll never find a kit anywhere that does more IOPS per DB CPU. So, look for somebody to prove me wrong. The whole point here is if you're testing your platform and your storage is more capable than your host, you're going to have a hard time because you won't have enough CPU to do the IOPS. But Slob resolves that problem for you because minimum DB CPU for maximum IOPS. But Slob is not limited to the functionality given by the defaults. Slob can do more. So those of you who know Slob see on the left, and I have no idea how visible that is out there. On the left, I can see it, so I'm enjoying my presentation. On the left, what you see is the typical Slob weight profile. So this is the section of AWR where you get to see the different weights and what % of DB time those weights are. So Slob, you should always see the first weight is DB file sequential read, or if you're running on Exadata, it will be cell single block read. And so here, according to my eyes, it's about 97%, and then the rest is all DB CPU. So this engine does I/O. Now on the right, that's actually Slob as well. I don't know if you can see it or not, but the weight events are in order: latch, row cache objects, then DB file sequential read, then cursor mutex X, and then library cache mutex X. That's not typical Slob, is it? Has anybody ever seen any of these weight events pop up in their production workloads? Oh, raise your hand, don't be shy. Yeah, these these weights, especially the ones that say concurrency as a class, they're busy weights, and it's important to understand how they work and how they impact performance. So I'm using Slob to help you learn how to draw focus on these busy weights. The way you do it is with Slob, you use the method in Slob 2.3 called hot schema. Okay, so on the right, I need my pointer. On the right, you see a snippet of the documentation, and it's got a representation of an Oracle table space. And in the table space, there are a bunch of schemas. And, right, so in each one of these schemas, and a Slob user has an amount of data, and the little red dash, well, that's also called hotspot. So every schema can have a hotspot, but the first schema in the database, that's also called hot schema. So the way this works is, as SQL is being churned through Slob, if you configure Slob appropriately, you can have N% of all of the transactions hit a user's hotspot, and M% of a user or all users' transactions fall back and hit the shared schema. So this would be a user that's got his own data and it's hot, and this would be a bunch of users that have shared data and it's hot. Okay, so that's called hot schema frequency. You set it with modular arithmetic in mind. Okay, has anybody here ever used Slob for contention, shared data, like in the multiple schema model? Yeah, Fritz, of course. So this is what the slob.conf looks like by default. But we're going to draw attention to two things. If you want to drive up contention with Slob, what you do is you enable the hot schema frequency. This says every 97th SQL statement that every user executes will fall back and use the shared schema. So it's a very infrequent trip through the shared schema. But you'll notice, compared to the previous slide, where I had my work unit set at 64, well, my work unit is smaller. This means that I actually execute more SQL statements, okay? Because every SQL statement goes after a smaller set of data. Your work unit size, that's the scope of the predicate for the Slob work unit. So it's like between M and N is the bounds on it. Well, the work unit will make that 8 times larger if you use the default Slob. So you're, instead of picking up only 8 blocks of data every SQL statement, you'll be picking up 64 blocks of data. What you want to do is you want to create contention. You want to shrink down the work unit so that you're pushing through more SQL per I/O. And that's how you get these odd increases in contention when you use Slob. So let's look at some data, right? So how about Slob executions as I ratchet up the hot schema frequency from modulo 2 to 97 and then never. So that would be the default. And here's how it graphs out. What am I looking at? So on the legend here, I can see that my blue line is DBCPU. And on the orange, it's physical reads. And everybody knows that with Slob, physical reads track executions very, very accurately. There's never a trip through a SQL execution where there's more or less physical I/O, because every block get is a physical I/O. Okay. So why do I have this very large and increasing amount of DBCPU, right? What's the value? The value is nearly 20. So that means on this box I've got 20 CPUs that are saturated and only doing 20,000 IOs here. 20,000 IOs with DBCPU of 18. That's not typical Slob. So what's going on here? I'm not doing any I/O, but I'm doing tons of CPU. That's bad, right? You want to get work done with less CPU. Where's all this coming from? This is the contention. I'm going to show you in the next slide. But so this is a loop where I say my hot schema frequency gets less frequent as I iterate through my loop. So here I'm out here about every third or so, right? Every third SQL statement uses the shared schema. Oh, and then I start to relax my DB CPU. So I'm using less DB CPU, but I'm getting significantly more IOPS. Where am I? It's extreme IO, so it's probably 400, yeah. So I'm 400,000 IOPS, right? And I'm actually using less DB CPU than I was when I was doing hardly any IOPS at all. So I'm just sitting there torching CPU and getting no work done. That's what these concurrency weights, the concurrency class weights are all about. They burn CPU and don't give you much payback. It's sort of like tax. Everybody does it, you don't get anything for it, right? Okay. Yeah, so here I varied through all of my tunables and produced a set of results where, now this is latch row cache objects as a percent of DB time. So imagine I've got a stack of AWR reports, and I go through and I pick out what latch row cache object is as the #1 weight event for these tests, and what percent of all DB time that is. So in the first sample here, it's 92% of all DB time. These sessions are doing nothing but row cache object spinning. They're thrashing, right? And as I experience a lower row cache object thrashing, what happens? I get more work done. Well, let's summarize that. Look at this. So a 50% reduction in latch row cache objects from here to here, that's only a 50% reduction in the percent of DB time that this weight accounts for, and yet performance increased 5-fold. These weights burn CPU, and CPU burning weights are extremely important to understand. So when you're testing on your platform, it's also good to test, for instance, rollout slob, and see if your platform can handle increased contention without going totally nosedived in latch row cache objects or cursor mutex X or any of these spinning weights, okay? So here's an example of where I take an Ivy Bridge host and compare it to a Haswell host. Now this is interesting because I don't change anything except for the host. It's the same storage, exact same application, same database, but I happen to have an older generation host and a new host. And what you can do in your environment, if you want to track new platforms as you take them on, keep some baselines of this stuff, right? So here you can see that my precise same slob contention testing exposed a lot of cursor mutex X in this range of thrashing, okay? But look, I switched over to the Haswell platform, and that entire weight event actually disappeared. The platform is more able to handle the contention. This is how, before you take on new hardware, keep these sorts of tests around so that you can know how it compares to the previous platform. That's one of the things that Slob is important for in platform acceptance. Okay, so what did I want to say about that? What's the point? You're all saying, what's the point? Yeah, what's the point? The point is busy weights suck. Now, busy weights are probably much more expensive than you think. You're looking at your AWR report and it's like, well, no, latch row cache objects is only 15% of my weights. Well, remember a few slides back where when it was 20% of weights, it affected performance by 3x, right? Don't equate the percentage relationship between these spinning weights. They're not even weights, really. I mean, they're non-orchestrated thrashing is what it is. Just be aware that the performance degradation doesn't track the percent of DB time, and that's what that previous slide was showing. And that you can use Slob, for instance, to research these kind of pathologies. That was the point. We made it through that. Now, on to the next one. Parallel query, CPU analysis. Why would I want to talk about something like this? Well, because there are a lot of misconceptions about modern host capabilities. These systems today are better than you think they are. I also feel that there's undue concern about the low-level SQL processing, the underpinnings on modern CPUs and modern platforms. So what I'm talking about is care and concern for how much CPU does it take to scan data? What if I lay on some filtration? What if I'm yanking columns out of rows? That's projection. Does this nuke my CPUs? Maybe not. So I say it's best to measure, and that's what we're going to look at here. The intent of this segment of the session is, let's look at some ways to investigate and attribute these costs to these underpinnings: scan, filtration, projection. I'll just use a simple table from TBCH. It's line items, about 90 bytes row, and I have 1 billion of them. And the way I measure what happened is I use $V systat, and I attribute I/O using that SQL statement. Everybody should believe that what that returns is an accurate answer, because it is. So this is how I measure how much I/O I did, and this is how I measure how much CPU it took me to do it. So if your session gets granted parallel query DOP of like 750 or something, that all gets costed to your SQL statement when you run this. So if you had 750 busy processes, the CPU they use gets charged to you here. So this is accurate stuff, it's good. But sometimes people say, well, I don't know, it might not be accurate, so I have to take a picture and show you something. Before I do that, I have to ask a question, because it's late in the day, it's been at least 30 minutes since you've had coffee, and the material is dry and boring. So let me ask, show of hands here, humor me. You have to handle 1 gigabyte per second of physical I/O with a table scan with Oracle. Does that take 5 modern processor cores? Does that take 10 modern processor cores? Does it take 1? Okay, that means everybody here is in one of 2 mindsets. Either they want me to hurry up so they can go out there and get the beef jerky and the free slob buttons, or you have absolutely no idea what the answer is, and that's good. That's good, because I can tell you. And in fact, I'll tell you how you can study this on your own platforms as well. But let's go back first and look at a picture. Okay, this is a single host, 2-socket Haswell, so it's like 2699 V3 CPUs, doing 6.2 gigabytes per second. And if you count from the right, and you look at the percent in user mode and percent in system mode, well, by golly, it's 4% of 72 threads. This is 1.4 cores knocking out 6.3 gigabytes per second. So I didn't offer that in the multiple choice because that's off the charts. Does anybody? No, I won't do the quiz. Here's the deal. A lot of people don't know this. A lot of people don't know that CPUs have nothing to do with the movement of this data. The CPUs are handling the opcodes that ask the OS to go and get the data, but they don't touch the blocks of data. No. Well, this is a count stars, so they do look at the block header because there's a row count in the block header, but that's loading 164-byte cache line from the top of the AK block. So here's the deal. There's all of these 1 megabyte reads coming in because they're multi-block reads. These 1 megabyte reads are coming in. The CPU doesn't touch the whole block, right? I mean, these systems use hardware device drivers and hardware that know how to do direct memory access. It's the device that simply jams the data from storage into memory and then tickles the CPU for an interrupt, and all that does is the kernel goes and says, oh, this process that made the call, he's now runnable. That's it. That's why it takes 1.4 cores out of this 36 core box to push 6.2, 6.3 gigabytes per second. And this is Oracle PQO. This is probably more performance from 1.4 cores than you would have expected, right? Humor me. Yes. Okay. I got there. Moving on. Well, you know, every now and again I have to show you the storage GUI. This is actually loading line item table. This is that same Haswell host. This is a 2-socket host. And if somebody walked up to you on the street and said, I've got a 2-socket server, it's a pizza box about yay big, and it can jam 7.2 gigabytes per second through storage networking to and from this array, would you have believed it? No. You would have said, that's foolishness. But actually it's true. These systems are much more capable than you know. And this is important. This way you don't have sort of a platform paranoia when you're looking at your performance data. Remember that these systems can do a lot more than you thought before you came in, and by the time you leave, you'll see some numbers. Continuing on. Parallel query, CPU. So here's what we're going to do. We're going to study CPU. We are going to look at lightweight scans. So this is, in this kind of performance engineering, this is called a lightweight scan. It's just count star. The reason it's lightweight is because the only data it looks at is the block header of every block to get the count of rows that are in the block. Then we're also going to look at a scan that looks at the first ordinal column. That's a little more intensive because instead of just taking an 8K block and peeking at the first 64 bytes of it, well, I've got a 90 byte row, so I have, by the time you shave off some fudge for percent free and this, that, and the other, there's about 75 rows or so in there. So if I tell my SQL that you have to jump out and find the left ordinal column for every row, well, he's jumping back and forth to some header information that says where the beginning of that row is, because there's accelerators that tell Oracle where the beginning of a row is, but there's not an accelerator that says where the beginning of every column is, because that would be too much block metadata and leave no room for data. So that's where a row walk comes in, because there's an accelerator that says where the beginning of the row is, and then he's got to go out and find the column that the SQL is addressing. But we're going to look at the first ordinal column. So it's just from the block map, boom, to the leftmost ordinal column and then back up. And so some additional CPU. You should expect to see more CPU utilization if you do that. Count star with predicate, where the selectivity is 0%. So all I'm doing is I'm saying apply the predicate, but I don't care about any of the counting of rows. I just want to predicate. Then I'm also going to look at a simple aggregate with no predicate. Count star after filtering all columns, so I'm forcing filtration of all columns, but the answer is yes on all of that, and I'm getting all the rows back. This will make sense in a moment. Then I have a SQL that ingests all columns with no filtration, and then I have one finally that filters all columns and ingests all rows. That's the full Monty.
We're going to see that?
The full Monty?
Yeah.
Where's Mullins? Okay, so this, yeah, he's out there. He's working at the full Monty. So this is a snippet of a full Excel spreadsheet that I have, and we'll look at that in a moment if we want to fill in some gaps. Here's how this goes. So what I have is the table is 1.2 terabytes. And it takes me from 206 seconds to 241 seconds to scan it, depending on how much of the data I'm mashing on, right? I do some math, and now I know my megabytes per second. Well, that one query that said how much my CPU was told me how many CPU seconds I used during this elapsed time. So now I know how many CPUs were fully saturated. So I've got that number here. And then to help the audience out, I flip that around and say, well, if I was thinking about adding units of I/O to my queries in increments of a gigabyte, how much more CPU would that take? So the way this goes is, if all you're doing is count star and you want to increase your I/O flow by another gigabyte, it'll only burn another 0.22 cores. And you can see that because 6.1 gigabytes per second burning 1.4, okay? So why is it that these queries here impact my throughput down from 6.2 down to 5.2 and 6.2 down to 5.5? That's because consumers always throttle producers. Oracle can't just go and scan data and not have any consumer of the data. The simplest consumer of the data is count star, which only looks at the block header. But these are very heavy consumers of data because they're saying, in this case, it's saying filter and ingest, and here it's saying just ingest, okay? So let's look at this. In order to do these very simple queries, I never burn more than 2.2 cores at 6.2 gigabytes per second. This means the most uninteresting thing you can do on a modern computer with Oracle is select count star or select count of any simple an aggregate of you know, no complexity, right? This is always going to give you the right answer, which is my computer is fast enough. That's not the answer you want. You want the answer that my computer might be fast enough. So what you do then is you take a look at this task. Now, this task is, well, gee whiz, I'm saying count the rows after you filter out all the data. But as I said in the previous slide, there's actually no data found. So what I'm seeing here is on my system, it takes 15.2 cores to filter all of this data. That data is flowing through at 5.5 gigabytes per second, and for every row, I'm looking at every column and I'm doing an evaluation. That's filtration intensive. It can't get any worse than that for filtration because you're looking at every single column. Then what I do is I shave off all that filtration, and I want to see how expensive it is if I just actually eat all the data. So I'm not filtering, I'm just ingesting the data. And the way you do that is you have to use an aggregate that will only return one row. So I use min, and then for data types that aren't appropriate, I'll just use one of the other handlers. Like for dates, I just say, give me the greatest of these three date columns, and then for the final result, I want the min of the greatest of all of those. So it's, you know, one row spits out, but the point being here is that this is no filtration. So all filtration is 15 cores, or 2.8 cores per gigabyte per second. That's all filtration. Only ingesting data is about the same. So the top half of the query takes about the same as the bottom half of the query. And oddly enough, when you sandwich them together, it takes the addition of the two. So here's the deal. You would say, well, gosh, Kevin, your system only has 36 cores. And I would say, you're right. I'm pushing through 5.2 gigabytes per second, and I'm doing crazy things like filtering varchar 40s and things of this nature. I'm being as heavy as I can on my SQL processing, and I'm still able to eat up 5.2 gigabytes per second, and I still have some SMT overhead, if you believe that SMT gives you anything. Because this is 34 of 36 cores. There's 72 threads on the system. So what you get to see when you do this kind of testing is you get to see, well, what's the worst it can be on my platform based on complexity, and what's it like in the middle, and what's it like at the top, and then you look at your queries and you say, well, I never do crazy things like where varchar 40 is like, you know, %Z%. Nobody filters like that. So you know that you picked it to be as bad as it could. This is actually a typo. That's %Z%. So what you do is you test for as bad as it could be, and then you contrast that to the actual kind of filtration that you do, and you get an idea. You know, you won't be surprised at the DB CPU that comes out of this kind of filtration, this kind of protection. How many people thought that you could cram 5.2 gigabytes per second through something that complex and only use 34 cores, right, 35 cores? That's probably more capable than you thought. Now, having said all of this, none of this matters. None of this matters one bit. You know why? Because the only thing that matters is joins and sorts. That's what burns your CPU. So that happens to be common on all platforms. Exadata. Best-of-breed systems like a Haswell system like this attached to pretty decent storage. So actually the way you look at this is you say, all of my CPU is going to hash and sort, hash join and sort anyways, or join of any type. All of my CPUs go into join and sort anyways. I don't need to be as paranoid about this as I probably was. You're more in this area. Let me show you the difference between filtering on the stupid varchars and not. This makes the point. All right. So the last three columns of the row are varchar. Now look, I was only using 14 cores to eat up 6.2 gigabytes per second. I was only using 14 cores, and still I started monkeying around with the varchars. You don't predicate on varchars. So really where you're at is kind of in this space here, where you can say, yeah, you know, 2.8 5 cores per gigabyte per second for doing reasonable filtration. You don't filter a varchar 40 and say percent something percent. It doesn't happen. But I wanted to put it in here so you can see where the me is, right? It's all nice and predictable as you add more and more data to ingest. It's nice and predictable until you get up to that stupid varchar stuff and it just goes off the handle. All right, what do we got left here? Oh, about another hour and 15 minutes, okay.
Kevin, isn't this like quantifying of gram systems is not all logical IOs are the same?
Well, yeah, that's most certainly true.
Like equating all logical IOs.
Well, I think really what this is all about is we're all too paranoid about what costs what. You know, we're you know it's like being paranoid about dying in a plane crash because that's gruesome, but it's not going to happen. You're going to die in a car crash. Right? It's human nature. It's human nature to fear the gruesome. And you know, people say, well, there's another platform like Exadata that does all this filtration off on some other CPUs. Well, these systems can handle the filtration. That's what I'm sort of preaching. All right, moving on. Okay, so I think this is my summary. Yeah, modern systems are capable of huge volumes of data flow, right? I mean, it's a 2-socket pizza box cramming 6.2 gigabytes per second through there. You saw another screenshot where 7.2 gigabytes per second because I was doing data loading, direct path, insert as select. And the thing that I'd like to recommend here is that you have your own schemas and you have your own queries. Look at your predicates and build models like this in test so that way, if you take on new hardware, you won't be surprised. You'll know how much it costs to scan through and filter in one of your more difficult queries. Shave the query in half, right? Write it so that it does all of the ingest without filtration, and then do it where it does all the filtration but doesn't ingest. Do these things, and then put the 2 slices of bread together for the whole sandwich, right? These are methods that help make sense as over time as you do different hardware updates and things of this nature. All right, a word about swing bench. I have 5 minutes. Here's the deal. I haven't said it yet in this presentation, but somebody, probably Fritz, wondering when I was going to say it. Everything is a CPU problem, right? You all know that, right? When you're talking to somebody over beers, another DBA, and you say you have an I/O problem, that's a CPU problem. Because you don't have good enough I/O to keep your CPUs busy. If you've got crappy code, you have a CPU problem. Because that code is burning too much DB CPU for the work you're getting done. Taxation without representation. Okay? Everything is a CPU problem. Here's what you do. You do what I did. Investigate swing bench using CPU affinity so that you can partition the foreground processes from the background processes. And then you look at what effect that has on I/O times. Hold it. All he's going to do is change where the processes run, which CPUs the processes run, and that will affect I/O times? Everything is a CPU problem. The way you do this is with NUMA CTL, Fizz CPU bind. You can say, what I'm about to run is pinned to logical CPUs 0 through 19, you won't do 20, 0 through 19, and then you start whatever that is. It could be a listener, and then therefore when you start your database through your listener, all of those processes now run on CPUs 0 through 19. And then you do the opposite of that with 21 through 39 on a 40 core box, or 40 SMT box. To run whatever, maybe the foreground processes. So whatever your script is that fires off all the SQL plus, and then therefore the foreground processes. That's how you can partition this stuff. You can do it with C groups and what have you as well. I didn't even have to show anything because I stated it right there. Everything's a CPU problem. what I'm showing you here is a whole bunch of data, and I'm going to put this in a blog post as well. This is a bunch of data, and it's probably an eye chart to you. So what I want to point out is that without affinity, and this is something else, without affinity, I get less physical I/O with higher latencies. You can see that up on the top row, where I have DB file sequential read latency and direct path read latency. And you can see that it's 735 and 1202, those are microseconds. Even though I'm only doing, go back to the left, I'm doing 57,500 physical IOs. Now, when I wrap this thing up in some CPU affinity, I actually come over here and I can do 73,000 physical IOs, and I'm doing it with less DB CPU, and look at my service times. I'm doing significantly more I/O, and yet my service times have dropped. Why is that? Because the time that processes spend on the run queue, waiting to actually do the instructions that close the timing on a wait event, that's charged against you. Everything is a CPU problem. So if your process spends a half of a millisecond runnable every now and again, because a time slice is 10 milliseconds, if that's at the end of physical I/O, that averages in, and you end up with CPU problems causing increased I/O waits. Okay? So look, without affinity, what you get is 21% less physical I/O, but it's actually taking more DB CPU. So what am I saying? Well, I can't tell you what I am saying. I know what I'm not saying. I'm not saying to go out and start your databases under this kind of hard affinity. But what I am saying is consider things like C groups, especially if you have a lot of different apps that are running on a host, because everybody runs with hyperthreading turned on, right? Well, the worst thing for hyperthreading is applications that are contending for data and not orchestrating that in any way. Because what you end up with is the holder of the resource is buried behind some process that's spinning on the resource. And the switching for SMT is either when a process stalls for a memory load, or if there's an end of a CPU time slice. So it could be just a few cycles of time that the holder of the resource is buried. It could just be a few cycles, or it could be milliseconds, okay? Especially when he's buried behind a process that's just sitting there spinning for the value to become false, and he's waiting for it to become false. That means the latch is not set. Well, he won't get on CPU until that guy exhausts all of his tests on it, and he goes off, he comes on, and then releases the latch. So the thing about SMT, that's the worst thing for SMT to do well at is high contention workloads. Every workload where you have concurrency class weights in the top 10, no, in the top, if you have concurrency class weights in the top 3, if you run that on a system that has SMT disabled in the BIOS, it will be faster. Always. That's because there's no orchestration. It's just blind spinning, and there's no way to make sure that these CPUs aren't accidentally doing what they're being told to do, which is run the guy that's not going to stall on memory when the guy that needs to release that resource to him is buried behind him. He's on the same core, but the thread is held down by the spinner. So I'm not saying do this stuff, but I like to point out that even when you're running applications that are, Swing Bench is good if you want to prove to yourself that Oracle is a suitable transaction engine. I accept that Oracle can do transactions pretty well. That's been established now for 11 years times 3 or something. So I don't need to prove to myself that Oracle can do transactions. I do platform work. You'll notice how many IOs I got, 73,000 IOs with DB CPU of 28. With Slob, you get around 11 to 12,000 IOs per DB CPU on every platform. So you'll never have enough CPU to saturate your storage with this workload kit because it's too transactional. But I like it to bring to mind things like, you see all of this log file sync piling up here. That's not actually because the storage is slow. It's because the CPUs are nuked. And you notice it improves when I partition off. I have LogWriter has his own CPU. That's what this incantation is here. So when I'm pushing 73,000 IOs, it's because all of the foreground processes, all of the swing branch processes are running on CPUs 0 through 34. LogWriter and Database Writer get the rest of the CPUs, so they're not being interrupted by anybody, nor are they interrupting anybody. It's just a partitioning of different kinds of processing on different CPUs. So yeah, consider C groups, and that is the end of the hour. Thank you so much.